Now we will characterize these random variables. So first characterization of random variables can be done by cumulative distribution function, which we also call CDF. And the CDF of a random variable x is defined as the probability law on the set minus infinity comma x, which is closed from side x. Okay. So remember minus infinity to x is a valid Borel set. So the probability x is defined on this, and this we call it fxx. So for any value x, the CDF is denoted as fxx, and is it equal to probability law x on minus infinity comma x. Okay, this is a capital X. This is capital X, which denotes the random variable x, and this x is a local variable which changes. So as x changes, this will be a function of x. So you can compute fx1, fx0 like this. So let us recall what is the value of this. Remember, probability law of any set B under X is equal to probability of X inverse of B. Okay, so the probability of this is equal to this function is equal to probability of X inverse of this set. And what is X inverse? Pre-image of this set. Pre-image is made from all those omegas such that X omega is element of this set. In other words, it means that all those outcomes which maps to this set, okay, which maps to one element of this set, will be included in the pre-image. And I want to compute the probability of that pre-image. So probability of set of all outcomes which map to this set, or in other words, probability of set of all outcomes for which x omega is in this set, that will be the CDF of random variable capital X at value x. Okay, and what does x omega belongs to this set means? It means x omega is less than or equal to x and more than minus infinity. So this is probability of this set of all omegas such that x omega is between x minus infinity and x. Okay, and sometimes people, in short, they remove this x omega. They just sometimes also say probability that capital X is less than or equal to small x, which is a short notation, which actually means that you want to talk about the probability of the set consisting of all omegas such that x omega is between minus infinity and x. Okay, so remember this particular object we have calculated for the example we have taken. Right? We have considered an example where we flip a coin, it can get head and tail, and we have mapped head and tail to 1 and 2. Right? So we have computed the probability law of this x. Right? So under this definition, fxs will actually be equal to whatever we have calculated. So simply probability of x we have calculated is this, that when x is less than 1, it is 0. When x is between 2 and 1, it is 1 by 4. And when x is greater than 2, greater or equal to 2, it is 1. Okay. So whenever the set includes 1, you add 1 by 4. And when it also includes 2, it includes 2, you add 3 by 4. And when it includes both, you add 1 by 4 and 3 by 4. So this will be the CDF of this random variable x. And if you plot it, it will look like this function. So up to 1, it is 0. Exactly at 1, it becomes 1 by 4, stays there until 2, and at 2, it becomes 1. Okay, so this is actually a discrete function with fixed two discontinuity, one at 1 and another at 2. Okay, so this is 1 and this is 2. So, right, and the final values becomes is 1. So this is one example of one random variable, and the CDF is given as this. So just applying the formula, we can calculate the CDF of any random variable. Okay, we assume the probability measure is already known. So we know the probability space omega fp is known. we know the probability measure on omega. And when we want to compute and a random variable is given, means a function is given which maps outcome to real numbers, and we want to compute CDF. So we just take sets of this size and apply compute pre-image, which will be a set of Borel algebra on omega, or sorry, which will be a element of sigma algebra of on omega, and then from that we can compute the probability, and that will be equal. So it's rather easy. You just take of all such sets -20, x to compute the pre-image for every x, and then from pre-image you just calculate the probability measure which would be given, which is already assigned. So that from that you can compute the CDF. Okay. So always remember, for probability to compute the CDF of random variable, you have to always go back to the original probability space, where the probability of different subsets of omega is given. So you find you are given any set -20, x. You find the pre-image, which will be a subset of capital omega, and then from there you find the probability of that. That will be your CDF at value x. Okay, so from CDF we actually put two more constraints on random variables. We say that random variable cannot take -infinity, and +infinity with non-zero probability. So x can take any value, but it cannot take -infinity or +infinity with non-zero probability. This means that probability of all omega says that x omega is -infinity, that should be 0. Right? So probability that x omega takes value -infinity, or in other words, probability of a set of all outcomes which maps to -infinity should be 0. Similarly, for +infinity also 0. Okay, so I'm not saying x omega cannot take value infinity -infinity. It can become infinity and -infinity, but it takes those value with 0 probability. It cannot take infinity -infinity values with non-zero probability. So this we say almost surely, right? Recall I said that if x takes some value, f satisfies some condition with uh, one probability, then we say it's almost surely occurs. So here all x is almost surely finite. It can be infinite, but probability that it will be infinite is 0. So which means x is finite with probability 1, which is other way to say x is almost surely finite. Okay, so recall this word almost surely. Almost surely means x satisfies some condition with probability 1. And if x satisfies some condition always, then that is always true. Then we don't have to say it's almost surely. But then we say x is finite. So let's talk about some properties of CDF, which will be useful. One is fxx CDF is a monotonically increasing function. It means if you take two elements x1 and x2, if x2 is more than x1, then fx2 should be more than or equal to fx1. It cannot decrease, it will increase. Okay. Also, it's not, I'm not saying strictly, because sometime it can stay equal, right? As the example you have seen here, this is a constant. It doesn't increase here, but it increases here. But it cannot decrease. Okay. So it either increases or stays the same, but it cannot decrease. So it's a monotonically increasing function. How do we prove this? Right. So let us take Ex is equal to pre-image of -infinity, x. Okay. So from this definition, we know that fxx1 is nothing but probability of Ex1. Okay. Because Ex1 is the pre-image of -infinity, x1, which is, and the probability of that is nothing but the fxx1 by the definition. Similarly, fxx2 is the probability that x omega is less than x2. And that is same as probability of pre-image of -infinity, x2, which is Ex2. So now what we note is that Ex2 is union of Ex1 and this set where which is made from all omega such that x omega is between xn and x2. Okay, x omega is greater than x1 and less than or equal to x2. Okay. How do we prove this? See, this is made from all omega such that x omega is less than or equal to x2. Okay, and I'm splitting into two parts. One I'm taking is which is a set made from all omega where x omega is less than x1, less than or equal to x1. Okay, so some elements are left because these are made from all elements which are less than or equal to x2, and this is made from all elements which are less than or equal to x1, right? So for all omega for which x omega is between x1 and x2 are left out. So if I add that component, I will get EX2. Okay. So these are the outcomes which map to a number less than x2. This maps to a number less than x1 because x1 is less than x2. You will have some leftover omegas which map to a number between x1 and x2. So that set is this one. If I take this set and this set, I get all omega which maps to a number less than x2, less than or equal to x2. Right. Then also let us convince ourselves that this set and this set is disjoint. Okay. So this is made from all omega which maps to a number less than or equal to x1, and this maps to all omega which maps elements to more than x1. Right. So of course a element cannot be common here and here because if the element is here, it should map to a number less than x1, and which does not belong to this set because this set has only omega which maps to number which maps to a number more than x. Okay, so these are disjoint sets, and the union of these two sets is EX2. Okay, so now from probability additivity problem, we know that if there are two disjoint sets E1 and E2, the probability of E1 union E2 is probability of E1 plus probability of E2. So therefore here also probability of EX2 is equal to probability of this set plus probability of EX1. Okay, now probability of EX1 is fxx1 and probability of EX2 is CDF at x2. So what we get is CDF at x2 is equal to CDF at x1 plus this probability. Okay, now we know that probability of any set is greater than or equal to 0. Okay, so this means this is a positive or 0 number. This is a number which is greater than or equal to 0. So if you add a greater than or equal to 0 to any number, you will get a number which is either equal to it or greater than this, right? So what you get is fx2 should be greater than or equal to fxx1. So this is the result we want to prove. Okay, so from this we get that it should see if you plot CDF with x, it should increase, or some place it can be constant, but it cannot decrease. Now, second property we want to show is that fx is right continuous, right? What is right continuous? If you remember, continuity means the limits are equal to the value at that point for any function. So right continuous means the right hand side limit, right? As you decrease the value x from a higher side to a value a, the limit of these values you are getting should be equal to the value at a. Then we say the function is right continuous at a. Okay, similarly left continuous also, if you want to see left continuity at a, you will take numbers less than a and you increase the x to a. And if that limit is equal to the value at a, you will call it left continuous. If both are same, then you say the left hand side limit is equal to right hand side limit, and that is equal to the function value at a, then the function is continuous. Okay, so we are not claiming that CDF is continuous. We have actually in fact seen that CDF was discontinuous in the previous example. But what we want to claim is fx is right continuous. It means if you lower the value to a number a, then the limit of the CDF should be equal to the value at a. Okay, in simple mathematical words, we can say that limit of CDF at x plus epsilon, where epsilon goes to 0, is equal to fxx, right? So we are looking at the value at numbers more than x, right? Little bit more than x, and we calculate the CDF. And we see that as we make that number close to x, this CDF converges to the value at x. Okay. So this means, in simple word, that suppose x is 1. It means if you look at the value of 1, and if you look at the value of 1 plus 0.00001, then those values should be close. And as you decrease further, the number should, the CDF value should come closer to the FO. Okay. While so there should not be any break from the right hand side, but there can be break from the left hand side. It means the value at 0.99999 and value at 1 can be different, right? Significantly different. One value can be 0, other value can be 1. But that cannot happen from the right hand side. The value should slowly change. Okay. The function should be continuous as we move from a higher number to that. There should not be a break. So how do we prove this? We will apply the one property we have learned. So let us see this, how we formally prove this. So I'll just go down the steps, and then you will understand what these steps are represents. So let E equal to a set of omega such that x omega is less than x plus e epsilon. So this is the pre-image of minus infinity to x plus epsilon. Okay, so I'm trying to find all outcomes which map under x to a number less than or equal to x plus epsilon. This will include x because this will include all omega which also maps to x, right? Because that they are mapping to a number less than x plus epsilon. Right. Now let us define a decreasing sequence of epsilon. So a sequence is in the form of epsilon 1, epsilon 2, epsilon 3 up to epsilon infinity, and we make sure that this sequence is decreasing. It means E n is less than E n minus 1, and the limit as n tends to infinity is 0. Right. So one such sequence can be 1, 1 by 2, 1 by 4, 1 by 8, like this. Right. There are many such examples where you can find a decreasing sequence which goes to 0. Right. So from each element epsilon I, let us define one set ei, which is made from all omega such that x omega is less than or equal to x plus epsilon I. Okay. So these are EIs. So EIs are pre-image of the set minus infinity comma x plus epsilon I. Right. And again, you can know since epsilons are positive number, right? It's a decreasing sequence, but it always is more than 0. So this set will always include x. Okay, and all the numbers below it. It will include all omegas which maps to a number x or a number lower than this. Okay. And they will of course include some more part depending on what is the value of epsilon I. So because the decreasing sequence of sets, you can say we found the countable intersection of EIs, and recall the countable intersection of EI is defined as a set of all omegas which are in all of EIs. Okay, and then you can prove that the intersection of this set is nothing but nothing but omega such that x omega is less than or equal to x. Okay, how do we prove this? You can take that if you take any number, if you say this is x, this set is equal to x omega less than x plus some number a, then you can prove that whatever a you take, you can always find epsilon such that epsilon I is less than a. Okay, so in that case, the a will not, x plus a will not be contained in EI. So if it is not contained in one of the EIs, it cannot be in the complete intersection. Okay, and the largest number which can be in all EIs is x. Okay, because EIs is not 0. So one element can always be there is x and all the numbers below it. Okay, similarly you can show that if I just take En, the intersection will be omega x omega less than x plus epsilon n, right? Right, why? Because E1 has x plus epsilon 1, then E2 has x plus epsilon 2. Now x plus epsilon 2 is less than x plus epsilon 1, okay? And they're decreasing sequence. So the intersection of this decreasing events is always the last element, last set, okay? So this is nothing but En. Now we know from probability, so these are countable intersection of EI. This is finite intersection of EIs. Now we know because they are equal, we can say probability of this is equal to probability of this. So probability of intersection of EIs is equal to probability of this. And what is the probability of this? This is nothing but fxx by definition. Similarly, probability of this is equal to probability of this, and this is nothing but probability fx at x plus epsilon by definition. Now, from property of probability measure, we know that this probability of countable intersection is equal to limit n tends to infinity probability of this finite intersection of first ENs. Okay, and what is the value of this is equal to fxs, and this is the value of this is fx is x plus epsilon n. So from this we have proved that the CDF at x is equal to the CDF of x plus epsilon n as n tends to infinity. Okay, in simple words, you can understand this way that suppose you want to see the continuity at x, right? Let's take a number larger than the x. Let's take x is equal to 1 and then take a number 2. Okay, so the value of CDF at 1 is equal to probability that the random variable, omega is such that omega maps to a number less than 1. Okay, now for 2 it will be the probability that of all omega such that x omega maps to number less than 2. Okay, and of course the difference would be the probability of all omega which maps to a number between 1 and 2, right? Now, so this is the probability of so the difference between the CDF at 2 and CDF at 1 is equal to probability probability of the set of omega which maps between 1 and 2. Okay, so this is probability x is between 1 and 2. Now, if you decrease 2, so this is the size of this set 1 comma 2. Now, if you decrease set 2, if you decrease, if you move from 2 to 1.5, right, then the difference between the CDF of 1.5 and CDF at 1 is just made from the probability of all our set of all outcomes which maps between 1 and 1.5. So it will decrease, right? If you keep on decreasing 1.4 to 1.1 and 1.01, right, the difference between the CDF of 1.01 and CDF of 1 will decrease, right? And if you make them as small as possible, then if you make them smaller, then the probability will further decrease and eventually goes to 0. Now, the third property of CDF which we want to say is that it made from two statements. One is as x goes to minus infinity, the CDF should go to 0, and as x goes to plus infinity, CDF should go to 1. Okay, so what we can see from here that CDF is an increasing function, and at minus infinity it is 0, and plus infinity it is 1. So a CDF goes from 0 to 1 and it increases from 0 to 1. Okay, in a way that's always right continuous at any point. Okay, so how do we prove this? First, we will let us understand what the statement means, right? So recall the fxx is nothing but the probability of the pre-image of minus infinity comma x. Okay, so it's a probability of that outcome maps to a value less than x. Okay, now if you keep on decreasing x, this number will keep on decreasing. So when x goes to minus infinity, this will be a pre-image of minus infinity comma minus infinity. Okay, which is actually a very it is an empty set because it doesn't include anything. If I ask you what is the number which is between minus infinity and minus infinity, there's no number, right? It's an empty set. So the pre-image of this empty set will also be empty. So probability of this will be 0. Similarly, as you move to plus infinity, this will be the CDF at x would be the pre-image of the set minus infinity comma infinity. So what is the pre-image of minus infinity comma infinity? What are the omegas which maps to a number between minus infinity and infinity? All omegas, right? All omega maps to a number between minus infinity and plus infinity. Okay, because this includes the whole real line. So if all omega are in the pre-image, then this pre-image is nothing but the complete sample space, capital omega. So probability of that pre-image would be probability of capital omega, which is 1. Okay. So how do I go ahead and formally prove this? We apply the same way. We say that there is a decreasing sequence x1, x2, x3, xn, such that xn now decrease to minus infinity as n tends to infinity. Okay. Then I can say that I can form the same EIs such that EI is equal to made from all omega such that x omega is less than xn. Okay, sorry, En is equal to set of all omega such that x omega is less than x. Now, if I take the intersection of all this Es, you get empty set, right? So how do we prove this? You can show that. So this is made from all omega which belongs to each of these sets. Okay, and then you can say no matter what number you take, you will can always find a xn which is less than that number. Okay, so that now so let's take 100, right? So you can always find one sequence xn which is less than 100, right? If you take xn equal to minus 100, right? Let's take xn equal to minus 10,000. Sorry, let's take x equal. Let's take a number a equal to minus 10,000, right? Then you can always find one n such that xn is less than minus 1,000, right? Why? Because if you can't find, then the limit cannot be minus infinity, and the limit will be more than 10,000, minus 10,000, right? So because the limit is minus 20, the sequence decreases to minus 20. There should be always one number which is arbitrarily close to minus infinity. So there should be always a number which is less than minus 10,000, right? So for that n, that set will not contain a minus 10,000. So you can say that for any number you take in, you can always find one xn such that this set does not contain that element. Okay, and because you can prove it for every number, it means this set does not contain any number. So this set is an empty set. Okay, now we can say from probability measure again that limit x tends to minus 20 fxx is nothing but limit n tends to infinity of fxs at xn. Okay, and fxs at xn is nothing but the intersection of all these sets omega and xn. And from probability property, we know this is equal to probability of in countable intersection of these sets, and countable intersection is finite. Sorry, phi empty set. So this is equal to p of phi, which is 0. Okay. So this basically means as you keep on decreasing xn, this set will become smaller and smaller, and eventually the probability of that set should be 0. Okay. So the fxs, because it represents the same thing, it should be 0. Similarly, you can show for the other way. You can take an increasing sequence xn such that xn tends to infinity. Then you can take the union of such sets, and you can say that the union is omega, right? Because no matter what number you take, let's take plus 10,000, then you can always find that you can find a xn which is more than 10,000. So this would be in that set, and the union is made from means countable union means that it is made from all omega which belongs to at least one of these sets. Okay, now we can say that probability of x tends to plus infinity. This should be plus infinity of xx is equal to limit n tends to infinity fx of xn, and that is equal to limit n tends to infinity probability of this. and this from the property of probability measure, this is equal to this, and this is nothing but omega, so this is probability of omega, which is 1. Okay. So recall that probability law defines a probability of any set in the codomain of the random variable function. So we will prove that it's a valid probability measure later on, but let us first see how we can calculate its value for different sets in Borel algebra on R. So first, what we know here right now, that probability law of any of the set of the form minus infinity to x is its CDF, fxx evaluated at x. Now let us take another form of set, which is semi-open, semi-closed sets of the form x1 comma x2. It is open from x1 and closed from x2. So this is the format we were earlier also taking when we were defining the Borel algebra. So we want to ask here, what is the probability of this set? Of course, we will assume that x2 is greater than x1. So we want to know the probability law on this interval x1 comma x2. To evaluate that, we will first notice that the set minus infinity comma x2 can be decomposed into two different sets, one of the form minus infinity comma x1, and then the remaining would be x1 to x2. And this second set will be open from x1 because we have already included x1 in the first set. And I have chosen this in this format to make sure that these two sets, minus infinity comma x1 and x1 comma x2, these two sets are disjoint. Now we want to claim that if you have this C equal to A union B, and A and B are disjoint, then the pre-image of C would be equal to pre-image of A union pre-image of B. So how we can prove this? It is rather intuitive to say that the pre-image of this set, which is given by this, is made from all omega which map to this set. Now all omega which map to this set can be decomposed into two parts. One would be all omega which maps to minus infinity comma x1, and then second remaining would be all omega which maps to x1 comma x2. If you combine these two, you will get all omega which map to minus infinity comma x2. So once we have shown this, we can now apply the probability property that the probability of this set is equal to probability of this set plus probability of this set. We can convince ourselves that these two are disjoints. Because if this is made from all omega which maps to a number less than x1, and this maps to a set this is made from all omega which maps to a number more than x1, and of course less than x2. So these two are disjoints. So from this we have applied the probability measure property, and now you can notice that this is the probability of the pre-image of this set. So this is nothing but the fx, the CDF of x calculated at x2. This is CDF of x calculated at x1, and this is the probability which we want to calculate. So you can say fx at x2 is equal to fx at x1 plus probability law on x1 comma x2. So from this we can get that probability law on this set is equal to the difference of the CDF evaluated at x2 and x1. So if you are given at the such kind of set, you can just compute the CDF at this and CDF at this, and you can calculate difference to get the probability law. So what does this statement generally means is just that x1 x2 is the probability corresponding to a small interval, while CDF at x2 is the probability calculated on minus infinity to x2. So if you take that set and remove the minus infinity to x1, you only get probability corresponding to x1 comma x2. And once we know this, we can know that if we are also given any countable union of sets of this form, we can also calculate it, assuming they are disjoint, by just the countable additivity property of this probability measure. So now let us move to another one. What about open sets? So what about the probability law on this set which is open from both sides, symmetric and X also? What we know that if this was closed, then this will be equal to CDF at X. But now it is closed from X. It means I want to know the probability law on this, which is equal to the probability of all omega which maps to this. Okay, but we are not including X, right? So if any omega is mapping to the value X, don't include that omega. Include rest of the omegas which map to a number less than X. So remember, we have dealt this thing in past, and the way we do it, we construct a, we represent this set in the form of a countable union or intersection of semi-open sets, because we know the probability law on all sets of the semi-closed format, which is closed from the right side and open from the left side. But we do not know about the open set. So if we can represent these open sets in the form of countable union, then there is some hope that we can apply the probability properties of probability measure on it. So first we notice that the set minus infinity comma x can be written as the countable union of these sets. What are this set? So every set is made from minus infinity comma x1 minus 1 upon n, right? So as you change n, as you increase n, this set will include more elements near x. So let's say n equal to 10, then this will be minus infinity to x minus 0.1. And if you make n equal to 100, this will have minus infinity x minus 0.01. So there are some more elements from 0.1 to 0.01 which are added. Right? And every time you are taking these unions, so as you increase n, your set will increase. So you can see that by making n arbitrarily large, you can make the right hand side, the upper limit of these intervals, very close to x. Right. Suppose you want that this set is 10 to power minus 5 distant with it. I mean, suppose you want that the upper limit of this set is only less than 10 to power minus 3 from x. Then you will take n equal to 1000. Right. But so by increasing n, you can make it arbitrarily closer to the value of x, but you can never make it x. No matter what value of n you take, this right hand side will never become equal to x. So the set will never include x. That is why it is open from x, but it will include every number which is less than x. By taking an appropriate n, you can prove that this will be included in all the sets with n greater than that value or more than that. So anyways, we have represented this. So now we can say that because these two sets are equal, so their probability measure will also be equal. So probability of this is equal to probability of this. Okay, so see that I am using a shorthand notation here. What I actually meant is this is a probability of the pre-image of this. Okay, or we should say it px. So it is the Px of minus infinity comma x, which is equal to the probability of the pre-image of this set. Now, so let me just say this is also x, this is x, this is x, and this is also x. So these are all probability laws on that. Right, and you can always think of the pre-image side. So you can say this is the probability law on this. So this will be equal to the probability of the pre-image of this set. Okay, because we haven't still proved that Px is a probability measure. So what we have to do is every time we see this probability law, we have to take in the domain of the probability measure, so that you can apply the properties of the original probability measure. Okay, so this is rather easier to say. I've used the shortcut here, but it should be interpreted in a way that this is the probability law of this, which is the probability of the pre-image of this. Okay, now you can show that pre-image of this union of this is equal to union of pre-images of this. Now, because it's the union of some sets, you can and probability of that, you can apply the property which we have proved earlier, that this will be equal to limit n tends to infinity probability of the finite union of the pre-images of these sets. Okay, and what is a finite union of this set? Assuming these are increasing, so the finite union up to n will be the last set, because that is the largest set. So that this will be equal to the pre-image of minus infinity comma x minus 1 upon n. Now this I know because this is a semi-closed set, and the probability of this is equal to CDF at x minus 1 upon n. So this is the limit n tends to infinity fx calculated at x minus 1 upon n. And this will be the left hand side limit of the CDF, right? Because you are increasing n and you are getting arbitrarily closer. This is same as the left hand side limit of the CDF, which we denote as fx x minus. X minus denotes that x is increasing from the negative side. Now let's see how do I calculate the probability law on singleton sets. So once we have computed the probability law on this closed set and this open set, it's rather easy to calculate the singleton set by noting that if you add singleton element x1 to this open interval, you will get minus infinity comma x1, the semi-closed interval, right? Also notice that this and this are disjoint. This means I can apply the probability measure on these. Okay, so I will follow the similar principle. First, I'll take the pre-image and then I apply the probability measure on that. So from that, you will get that probability of the pre-image of this plus probability of the pre-image of this is equal to probability of the pre-image of this. So probability of probability law, which will be probability law, which will of minus infinity comma x1 plus probability law of x1 is equal to probability law on minus infinity comma x1. So now I know about this. This is the left hand side limit of the CDF at x1. This is the CDF at x1. So this will be equal to the CDF at x1 minus the left hand side limit of the x1. CDF at x1. So what do you understand from this? That if the function is left continuous, it means the left hand side limit is equal to the CDF value, then these two would be equal and this will be 0. So if CDF is continuous, left continuous at a point x, then the probability of the singleton set containing x is 0. Okay, so this means that if you just take minus infinity to x without considering x, and if you add singleton x, singleton element x to get the semi-closed interval, the probability is not changing between these two sets. It means by adding x, you are not adding anything to the probability. But if there is a difference, then you will add the element. Then you will get that element will have some probability. So now the remaining is to prove that this probability law is also a probability measure. And then we don't have to convert it every time to the pre-image. We don't have to take pre-image every time and then prove on the probability measure that this is true. So for that, once we have proved that this is a probability law, is also a probability measure, then we can directly deal with these new sets. So how do we prove that this probability law is also a probability measure? So let us first clarify, write it mathematically, that omega fp is a probability space, let x be a random variable. Then the probability law px of x is a probability measure on RBR. For this, we need to show that the probability law of empty set is 0. How do we prove this? So probability law of empty set is equal to probability of pre-image of phi. And then you can show the pre-image of phi is phi itself. So because if you want that the numbers will map to something, and if you want number doesn't map to any set, then of course those number there are no such numbers. So it should be the pre-image should be the empty set. So the probability measure of the empty set is 0 on the original probability measure. So probability law is also 0. Similarly, here in this case is complete, and for the new probability measure, the complete spaces are. So you have to prove that probability law on this real line is 1. And that is easy to prove because you have to take the this is equal to probability measure on original probability measure of the pre-image of R, which is made from all omega, which maps to a number in real line, which are all omegas. So the probability measure of complete omega is 1. So that's why you get 1. The third is let A1, A2, An are disjoint Borel sets, then the probability law of the countable union of AIs is equal to the summation of the probability of the individual law of the individual AIs. So for this, you have to write a similar argument. You can first think from the A1 and A2 perspective. If A1 and A2 are disjoint, then and suppose A1 union A2 is equal to A, then you can show the pre-image of A1 union pre-image of A2 is also equal to pre-image of A. Then you can apply the probability measure, and then you can show the probability measure of pre-image of A1 plus probability measure of pre-image of A2 is equal to probability measure of the pre-image of A1 union A2. Right? And what are these probability measure of pre-image? They are probability law. So what we have proved is probability law of A1 plus probability law of A2 is equal to probability law of A1 union A2. These can be extended to the countable union to prove this. So I'm not covering this completely, but this can be constructed very easily by proving that the countable union also, the pre-image of the countable union is also can be written as the countable union of the pre-image of individual sets. And then you can apply the original probability measure and then equivalent probability law definition. If you can convert them to that, you will get this third property also. So once we have proved these three properties, we now know the probability law is also a probability measure on RBR. And then you don't have to go back every time to the pre-image set. You can directly apply these things as if you have applied the original probability measure.